Great. Yes, my name is Chris Bunch, and I'm here today to talk to you about Neptune, a domain-specific language for deploying high-performance computing apps on cloud platforms. This is joint research between us at UCSB, Santa Barbara, and JPL NASA. Okay, let's start off by defining the ever so nebulous phrase cloud computing for us to get on the same page. As far as we're concerned, cloud computing is a service-oriented methodology by which some provider can offer some resources to you at some level of abstraction. In the cloud computing space, we typically define 3 layers of abstraction, each building upon the last. On the lowest level of abstraction is what we call infrastructure as a service, by which some provider will offer you some kind of scalable infrastructure. Typically, this means a virtual machine. Amazon is the first provider in this field, and they offer hourly rates for you can rent virtual machines on. This is entirely customer self-service. You acquire some virtual machine, you write some software, and it has to make the best use of this as it can. Scalability is offered here in the sense that you could elastically grow and shrink your application by acquiring more virtual machines, but there's no automation in this. You acquire the virtual machines, and your application has to be aware that there are other machines joining and entering the fray. At a higher level of abstraction exists what we call platform as a service, by which a set of scalable APIs are offered to the user. Google is the big provider in this area right now. Microsoft also has an Azure offering, by which, in the case of Google App Engine, Python and Java APIs are offered. You write an application, and as long as it uses these APIs, there is the promise of scale behind it. For Microsoft Azure, they use the .NET framework. At the highest level of abstraction is what we call software as a service, by which a single application is customized for use by a particular set of users. So these applications offered by people like Salesforce can be rebranded, repackaged, and given out to new customers, but fundamentally it's one application. So a trend that we saw over and over again is that largely in the cloud computing space, these problems have been solved for web applications. And while web applications are cool, we wanted to be able to take this to a completely different direction. Here, high-performance computing. We wanted to see what particular obstacles were in the way of making HPC really easy for the average user. The big thing that we saw is that the conception of who your target user is very different. In the HPC world, you're targeting the geek community largely, so you have users who are expert users. They're sometimes at the level of system administrators. If they want to run MPI, they know how to start up NFS. They know how to browse configuration files. They know all the specific dependencies on all the machines, and they can start it up automatically on their own. This is way different than what the cloud computing model offers. In the cloud computing model, anybody with a credit card can get access to these machines. So the barrier to entry is much, much lower. And as a result, you have people who have MPI code or want to learn MPI or MapReduce or whatever, but they don't want to muck around with learning NFS, learning all the configuration files. They just want to write some code and run it and call it a day. And as far as I'm concerned, nothing wrong with that at all. From a more cloud-specific standpoint, the abstraction that the cloud gives you is opaque by nature. You're not supposed to know where these machines are. You're not supposed to know how they're networked with each other. It's supposed to be safely hidden away from view. And this is the exact opposite of the grid world. In the grid world, you know where the machines are. They're supposed to be hooked up, usually, if you guess, with an InfiniBand network to get the best performance out of the system. These are completely antithetical to each other. Finally, because cloud computing is a relatively new space, there are many different providers out there, each with their own API that they say is the best thing you need to use it. This generates a bit of a lock-in, not as far as the actual app is concerned, but as far as the time investment is concerned. If I have a scientist who wants to learn how to use the cloud, they're going to spend some time sinking into Amazon's APIs or Google's APIs. And if they want to port from one provider to another, they're going to have to learn all these APIs all over again. Even when the APIs may be very similar or conceptually have the same service, that is storage, computation, queues, etc. So, to mitigate this problem, or to solve this problem, we have introduced a domain-specific language we call Neptune, which will automatically configure and deploy your high-performance computing applications. In scenarios where you can't get high performance out of the system for some reason, we also try to mitigate the problem of high throughput computing. So you give us many jobs, we try to run as many of them in parallel as possible, as well as the ability to run many different kinds of tasks. So it's not enough for us to simply say we solve MPI or MapReduce. There has to be enough offerings where we can say we are many task computing. As far as the implementation of Neptune goes, it is part language component and part runtime component. But what does that mean? Specifically, the language component is a number of meta-programming extensions to the Ruby programming language. It's essentially a superset of Ruby. We have tacked on some extra methods, some extra things here and there that you can use, specifically geared toward the HPC jobs. All of these language components we'll call the runtime component, which actually is a cloud platform. We specifically chose the cloud platform as compared to any other type of abstraction layer because at the infrastructure level, you can only control the virtual machine. And we want to do more than that. We want to control virtual machines, but we also want to control what software is installed on these boxes, what versions of software are installed in these boxes, so that I can take your code, find the right version of MPI, MapReduce, whatever, and hook it up and get your code running for you. So for us, Neptune is essentially offering scalable APIs to these services. So that puts us very nicely in the cloud platform layer. As far as Neptune can run, you can invoke it as some executable, give it whatever code you want, or since it's a superset of Ruby, you can pull it in as a library within your existing Ruby code. As far as the syntax of Neptune jobs look like, this is it. You tell us what kind of job you want to run. You tell us also what parameters your job needs to run. It's a piece of Neptune code is more than a series of just Neptune blocks over and over again. Like we said, it's a superset of Ruby, so you can pull in any Ruby code anywhere you want, print output to the screen, ask the user for some advice, what they want to do, and so on. As far as these parameters go that I talked about on the last slide, the parameters, it's not one set of parameters for every type of job until the end of time. And this is by design. We saw that when you're invoking an MPI job, the parameters you want to give it are very different from a MapReduce job or are very different from, let's say, an IBM X10 job a little bit later. We want to be able to say, only give us the parameters that your job needs and nothing more. We're not going to try to pigeonhole a common set of parameters into one small little space. We leverage Ruby's dynamic typing so that you can tell us these parameters can be an integer, they can be a hash, and I can take specific steps on my execution based on what type I'm receiving. We also want Neptune to be extensible. MPI is great, MapReduce is great. Neither of them are the end of the world, and neither are the juxtaposition of them. We want you to be able to add your own types of jobs so that you can automate running these for the average user, or a user who just doesn't have the particular amount of domain-specific knowledge that you have. All Neptune jobs return a hash map, dictionary, whatever you want to call it. They have a result field that will tell you if your job succeeded or not, and then the set of remaining fields are specific to your job. If you're running some kind of computational job, it'll tell you why your job failed if it failed. If you succeeded, like if you're wanting to do an input or an output job, or if you want to set some kind of data access policy, they won't tell you anything job specific because there's no job that's particularly involved here. And like we said before, this is extensible. You can add your own types of fields based on your own types of jobs. One question we heard over and over again when we started this project was, why not just use XML? There are lots of other things out there. They use XML, YAML, some other kind of markup language. Why not just do the same thing? And the train of thought that we came along to was, we wanted to be able to control the execution of this code. We didn't want to have just some markup language that your application has to consume and call it and write a file and make its own libraries and so on. We wanted to have something that if I had a Ruby on Rails app or some kind of web application, that I could easily go, say, run an MPI job, 16 machines, and have that go run in the background, and not have to worry about all these other kinds of configuration files that I want to write. The point of Neptune is to eliminate configuration files. So I don't want to introduce another kind of configuration file for you to write. Finally, I also wanted to be able to reuse code types within Neptune itself. So many HPC jobs obviously have the notion of input, output, data access policies. So I wanted to be able to reuse this and not have to make you re-implement this all the time. As far as the minimum set of primitive operations required to run your job, we modeled this on the portable batch system, PBS, found in the grid world. And the primitives are, get some boxes, run my code on it, give me the output. I don't care how it's done, just have these three primitives somehow. We decided to leverage the SoCal cloud platform, which we previously developed at UCSB, to handle all the configuration and deployment of that. So a quick diversion into that may be useful. SoCal is an open source implementation of the Google App Engine APIs. So what this means is Google App Engine gives you Python and Java code, has some